A few hours ago, most people driving through Cajon Pass had no idea they were crossing one of the most consequential pieces of ground in America. Trucks kept moving, trains kept cutting through the mountain corridor, power lines, pipelines, highways, and freight routes kept doing what they always do. Nothing on the surface looked different. No sirens, no collapsing roads, no dramatic crack ripping across the desert. And yet, according to one of the most important new earthquake studies to come out of Southern California, the deeper story beneath that narrow gateway has shifted into a state scientists consider profoundly concerning. Because this is not just another story about the San Andreas fault being dangerous. Everyone already knows the San Andreas is dangerous. The real story is more specific, more technical, and in many ways more unsettling. At Cajon Pass, the southern San Andreas fault system and the San Jacinto fault system approach each other in a tectonic knot northeast of Los Angeles. And new modeling suggests this junction may now be sitting in the kind of stress configuration that, in the past, has allowed a rupture to stop being one earthquake and become something much larger. Not merely a break on one fault, but a through-going event involving both systems. That is the idea reshaping how scientists are talking about this corridor. Not that an earthquake has been predicted, not that disaster is guaranteed tomorrow, but that one of California's most critical fault junctions may be entering the kind of loaded state where the gate no longer behaves like a barrier. That is exactly why the title matters. California's deadliest fault junction just unlocked is not really about a door flying open underground. It is about a geological switch point. A place where stress, timing, geometry, and fault interaction can decide whether a future rupture dies out, turns, or jumps. For years, the public conversation around California earthquakes has often been flattened into one phrase, the big one. But science keeps showing that the more important question is not just how big the next earthquake could be, it is how it propagates, where it starts, what other segments are already primed, which junctions can transfer rupture instead of trapping it. And right now, Cajon Pass is back in the spotlight because a new 1,000-year stress reconstruction suggests the answer may be moving in the wrong direction. To understand why that is alarming, you have to begin with the landscape itself. Cajon Pass is not just a geologic feature on a map. It is one of Southern California's great choke points, a mountain corridor linking the Los Angeles basin with the Mojave Desert and the wider interior of the American West. Interstate traffic flows through it. Freight flows through it. Rail lines cut through it. Energy infrastructure crosses it. In ordinary life, it is a transportation artery. In tectonic terms, it is something else entirely. It is a place where fault geometry becomes consequence, where the arrangement of the San Andreas and San Jacinto systems creates a structural problem scientists have been trying to understand for decades. Will a major rupture arriving at this junction keep going, or will the complexity of the fault network break its momentum? That question is not academic. Millions of people live in the answer. The new study, published in the Journal of Geophysical Research, Solid Earth, approached that question by stepping back from headlines and doing something much more powerful. Instead of looking at only recent quakes, researchers built a physics-based earthquake cycle model and fed it roughly 1,000 years of earthquake history reconstructed from paleoseismic evidence, including geological records, displaced sediments, tree ring anomalies, radiocarbon constraints, and documented past ruptures. Then they simulated how stress accumulated, relaxed, transferred, and reloaded across the southern San Andreas and San Jacinto systems through time. In other words, they tried to see today's fault conditions not as an isolated snapshot, but as the latest frame in a 1,000-year sequence. And what they found is the part that should make everyone slow down and pay attention. According to the model, tectonic stress along these systems has now reached, and in some places exceeded, the highest level seen anywhere in that 1,000-year simulation. That does not mean the ground must break immediately, but it does mean the regional system is not sitting in some average or ordinary state. It is sitting near the upper end of what this reconstruction suggests the region has experienced in the last millennium. In the San Jacinto Bernardino section, the modeled stress reached 3.6 megapascals, the highest value seen in the entire simulation. On the neighboring Mojave south segment of the San Andreas, it reached 2.8 megapascals. Those are not just big numbers for the sake of drama. They matter because the relative alignment between those stresses appears to influence whether Cajon Pass behaves like a stopper or a bridge. That is the first major rehook in the story. Because the danger here is not simply that one fault is stressed. Scientists have known for a long time that Southern California stores enormous tectonic energy. What is changing the conversation is the possibility that two major fault systems may now be stressed in a way that resembles the kind of setup that historically favored joint rupture. The study describes Cajon Pass as an earthquake gate. That phrase sounds cinematic, but in this case, it is also scientifically useful. A gate is not always open, and it is not always closed. It responds to conditions. When the stress states on the two connected systems evolve out of step, ruptures are more likely to terminate at the junction. When those stress states rise in concert and become more closely aligned, the conditions become more favorable for a rupture to propagate through the junction and involve both systems. And that one idea changes the scale of the threat completely, because a rupture confined to one system is one scenario. A rupture that crosses the junction and involves both the San Andreas and San Jacinto is another. The study explicitly warns that a joint rupture through Cajon Pass would likely be much more severe than an event limited to a single fault. The affected region is not some remote, uninhabited geologic laboratory. It includes some of the most densely populated infrastructure-critical corridors in the United States, including the greater Los Angeles area, San Bernardino, Riverside, and the Coachella Valley. The pass itself carries highways, rail networks, and energy corridors that tie the region together. So when scientists say this junction matters, they are not speaking in abstract tectonic poetry. They are talking about one of the places where geology and modern civilization are stacked directly on top of each other. But there is another layer to this, and it may be the most important one for your viewers. People often think the most frightening earthquake story is the one that says scientists have discovered something entirely new and bizarre. In reality, the most credible earthquake stories are usually the ones where scientists refine how an old danger actually works. That is exactly what is happening here. Nobody just discovered the San Andreas fault. Nobody suddenly learned that Southern California can produce destructive earthquakes. The deeper shock is that better modeling is now suggesting the region may be closer to one of its worst multi-fault configurations than many people appreciated. Not because the fault changed yesterday in some visible way, but because the long buildup of stress may now be reaching a historically significant alignment. This is where a strong script has to slow down for a moment and make the science intuitive. Imagine two separate but connected lines of weakness in the crust. Both are capable of slipping. Both are part of a broader plate boundary system that accommodates the movement between the Pacific plate and the North American plate. Now imagine stress building unevenly across those lines over centuries. Sometimes one is more ready than the other. Sometimes the geometry and local conditions favor rupture stopping at a structural complication. But if both systems enter a phase where they are highly loaded at the same time, the junction between them becomes less like a dead end and more like a transfer point. That is the essence of the earthquake gate concept. The gate does not predict the next event. It tells us what kind of event the system may be physically capable of supporting. And if that sounds subtle, it should. This is not a prediction paper. The lead researchers have been very clear about that. The study does not tell us when the next major earthquake will happen. It does not say tomorrow, next month, or even next decade. What it says is that the system is critically stressed, that present-day loading is exceptionally high in the context of the last 1,000 years, and that the current relative stress conditions between key segments are approaching the range historically associated with larger through-going ruptures. That distinction matters. Serious science does not need to promise a date to be alarming. In many ways, it becomes more alarming when the language is careful, because careful language is exactly what remains after sensationalism has been stripped away. This is also why the current title works for your channel if it is framed the right way. GeoPlanet performs best when the headline creates urgency, but the script earns trust. Your audience clicks for danger, but they stay for clarity. So the strongest version of this story is not to pretend scientists literally watch the junction unlock in real time. It is to take that emotional idea and translate it into the actual scientific shift. California's most dangerous fault junction may now be sitting in a critically aligned stress state after more than 160 years since the last major rupture to affect the wider Los Angeles region. That is not weaker than the viral packaging. It is stronger because it gives the viewer the feeling that the headline is being decoded, not exposed as fake. And the historical context makes the whole story heavier. The wider Los Angeles region has not experienced a major event on the scale of the 1857 Fort Tejon earthquake since, and that quake, estimated around magnitude 7.9, famously ruptured the San Andreas but terminated at Cajon Pass rather than continuing onto the San Jacinto system. In the framework of the new study, that is one historical example of the gate behaving as a boundary, but there is another example that points the other way. The 1812 Wrightwood earthquake is interpreted as a through-going event that crossed the junction and involved both systems. In other words, the geological record suggests both behaviors are possible. Cajon Pass has acted as a stop before, and it has acted as a transfer point before. That is exactly why present-day stress alignment matters so much. That becomes the second major rehook. Because once viewers understand that both outcomes already exist in the historical and paleoseismic record, the question is no longer whether a junction like this can ever transmit a rupture. It clearly can. The question becomes whether today's system looks more like a state that traps a rupture or a state that can pass one through. And according to the model, the answer is not comforting. The relative stress conditions on the San Andreas Mojave South segment and the San Jacinto Bernardino segment are now unusually high and unusually similar, which is the kind of setup that has historically preceded the more dangerous scenario. At this point, many viewers will naturally ask the question that always emerges in California earthquake discussions. Does this mean the big one is imminent, and this is where the script has to be disciplined? The honest answer is no one can say that. Earthquake science is exceptionally good at identifying where strain accumulates, which segments are hazardous, how past ruptures behaved, and what kinds of physical scenarios are plausible. It is still not able to tell the public exactly when a major fault will break. That uncertainty is not a weakness of the study. It is the reality of earthquake processes. The crust does not owe us a schedule. A critically loaded system can remain quiet longer than people expect. It can also fail in a sequence of ways people do not anticipate. The point of this research is not to forecast a day. The point is to improve the realism of hazard assessment. And hazard assessment in Southern California is not a side issue. It affects infrastructure design, emergency planning, insurance assumptions, corridor vulnerability, transportation redundancy, and how agencies think about cascading disruption. If a major rupture stays confined, one set of impacts is expected. If it crosses the gate and links both systems, another set of consequences comes into view. Ground shaking patterns can broaden, rupture length can increase, the set of communities exposed to severe shaking expands. Critical transportation and logistics corridors may be hit harder, and the psychological shock to the public becomes greater because the event no longer fits the simpler mental model of one fault, one rupture, one damage footprint. That is one reason this paper matters beyond the academic community. It reframes Cajon Pass not as a passive map feature, but as an active control point in Southern California's seismic system. The researchers did not simply calculate one present-day stress number and stop there. They modeled the evolving interaction of stress accumulation, stress transfer from past earthquakes, and even viscoelastic relaxation in deeper crustal layers between events. That matters because the crust is not just loading like a static spring. Every earthquake changes the stress field around it. Quiet decades do not mean nothing is happening. Deep layers respond, neighboring segments are nudged, structural complexity matters. The current state of the system is the result of centuries of loading and interaction, not just the passage of time since 1857. There is also an important geographical nuance here that deserves attention. The highest long-term stress accumulation in the model occurs north of Cajon Pass, around roughly 1.8 megapascals per 100 years, because of greater slip rates. South of Cajon Pass, the accumulation rates are lower, on the order of roughly 1.0 to 1.5 megapascals per 100 years. That asymmetry matters, because it helps explain why this junction is so sensitive. It is not merely sitting between two identical systems. It sits inside a complex network where loading rates, structural geometry, and rupture histories differ from segment to segment. That is precisely the kind of environment where a junction can become decisive. And this is where viewers usually start to realize that the most dangerous thing about California earthquakes may not be raw magnitude alone. It may be connectivity. A fault system with branches, junctions, stepovers, and linked segments can behave in ways the public does not intuitively visualize. A single segment does not have to carry the whole story by itself. The real hazard can come from how rupture interacts with complexity. Another USGS publication released this year reinforced that point by showing that high accumulated shear traction may encourage longer rupture propagation, but geometry still influences whether a rupture can overcome branches and stepovers. That means the future of a major earthquake in Southern California may be decided not only by how much stress exists, but by whether that stress meets the right structural pathway at the wrong time. That idea should completely change how your audience thinks about the phrase deadliest fault junction. The phrase is not saying Cajon Pass is the only dangerous place in California. It is saying that this specific junction may control whether the next truly catastrophic Southern California scenario remains confined or expands. Think about the difference between a fire hitting one structure and a fire finding a corridor that lets it jump into a second structure. The corridor is not dangerous because it burns by itself. It is dangerous because it allows consequence to multiply. That is what a fault junction can do in a multi-fault system. It can change the scale of the event. And if that sounds like a script built entirely on one fresh paper, it is not. The power of this story is that it sits at the intersection of peer-reviewed modeling, historical rupture interpretation, and the existing public awareness that the southern San Andreas region has been quiet for a long time. The new study simply tightens those threads into something sharper. More than 160 years have elapsed since the last major rupture to affect the wider Los Angeles region. Stress that would normally be released in large earthquakes appears, in the model, to have continued accumulating. And the junction that can determine whether two massive fault systems rupture together now appears to be in a critically loaded configuration. None of those pieces alone are enough to prove what happens next. Together, they are enough to justify serious alarm. This is also where the script can widen emotionally without sacrificing accuracy. Because California has a strange relationship with earthquake risk. On one hand, people know it is real. Earthquakes are part of the state's identity. On the other hand, familiarity breeds a kind of numbness. The threat becomes background noise. The San Andreas becomes less a physical system than a cultural symbol. But the ground does not care what has become normal to us. Stress continues to accumulate whether the public is paying attention or not. And one reason papers like this land so hard is that they force a dormant threat back into mechanical focus. They remind us that quiet is not safety. Quiet can simply be loading. That sentence may be the deepest emotional core of the whole story. Quiet is not safety. Quiet can be loading. Nothing dramatic needs to happen on the surface for the underground balance to become more dangerous. The mountain corridor can look calm. Commutes can continue. Real estate can keep selling. Warehouses can keep expanding. Yet underneath all of it, the relative stress conditions between two major fault systems may be converging toward the kind of configuration that historically allows a rupture to become regionally transformative. And because your audience responds strongly to investigative storytelling, this is a good point to zoom in on the words researchers themselves are using. They describe the system as critically stressed. They say present-day loading has reached or exceeded the highest levels of the past 1,000 years. They say the region may be capable of a large through-going rupture involving both fault systems. They say Cajon Pass can act as an earthquake gate. They say that right now the stress conditions between the two systems are approaching the range associated with major ruptures that cross both faults simultaneously. Those are not casual phrases. They are the restrained vocabulary of scientists trying very hard not to overstate what they cannot prove, while still making clear that the scenario space is becoming more severe. This gives you another rehook, because the story stops being about one number and becomes about one configuration. A lot of viral science content makes the mistake of assuming viewers only need one shocking metric. But people stay longer when they feel a system clicking into place in their minds. Here, the system is this: a 1,000-year model, record-level present stress, a historically important junction, two major faults loaded at similarly high levels, a mechanism that can either stop or transfer rupture, and densely populated infrastructure corridors lying directly in the path of the worst-case interaction. That is not one scary fact. That is a chain. And good retention comes from letting each link make the next one feel inevitable. Now, there is one more point that elevates the seriousness of this story. The study is useful not only because it says the region is highly stressed, but because it provides a framework for understanding why some past earthquakes propagated the way they did. That matters because earthquake hazard is not just about average recurrence intervals or abstract probabilities. It is about mechanics. Why did one rupture stop? Why did another continue? Why do some complex fault networks inhibit failure while others transmit it? The more scientists can answer those questions, the more realistic scenario planning becomes. In that sense, the Cajon Pass paper is not just a warning. It is a roadmap for how to think about multi-fault risk in California and beyond. And beyond is important because the researchers note that the modeling framework is not just applicable to Southern California. Complex fault junctions exist worldwide. Many urban regions sit near networks where multiple active structures interact. So what is being learned here is part of a larger shift in earthquake science. We are moving away from seeing faults as isolated lines and toward seeing them as coupled systems. That shift makes hazard models harder, but it also makes them more honest. Nature does not organize itself according to the neat boundaries on older hazard maps. Stress moves through systems. Junctions matter. History echoes forward. Still, for your channel, the local consequence is what gives the title its punch. Southern California is not just densely populated, it is densely interconnected. Los Angeles, San Bernardino, Riverside, and the Coachella Valley are tied together through transport, logistics, utilities, and economic dependence. Cajon Pass itself is one of the great infrastructure funnels of the region. So when a study suggests that the junction underlying that corridor may be entering a state more favorable to joint rupture, the word alarming becomes fully justified. Not because scientists are panicking, but because even a low-frequency, hard-to-time event becomes a much bigger planning problem when the mechanism points toward regional coupling. This is exactly why professional earthquake communication always walks a narrow line. Say too little and the public treats the danger as remote background noise. Say too much and it turns into empty apocalypse talk that people stop trusting. The best scripts live in the middle. They let the science create the fear. And here, the science does more than enough. The critical junction between the San Andreas and San Jacinto systems, the highest modeled stress state in 1,000 years. More than a century and a half since the last major rupture in the wider region. A history showing that this junction can either halt or transmit major failure, and present conditions that look uncomfortably compatible with the more destructive option. There is one final misconception worth confronting before the end. Some viewers hear a story like this and assume scientists are saying a giant earthquake is overdue in the simplistic sense, as if nature follows a missed appointment. That is not what the evidence says. Faults do not explode because a calendar page turned. What the evidence says is more nuanced and, in some ways, more chilling. The system has accumulated extraordinary stress. The quiet interval has been long. The junction that can determine whether failure remains limited or becomes much larger now appears to be critically configured. That does not guarantee timing. It guarantees seriousness. That may be the strongest ending point of all. California's deadliest fault junction did not unlock in the sense of a dramatic movie moment. It unlocked in the way real danger often does. Quietly, mathematically, historically, through the accumulation of conditions. 1,000 years of earthquake memory fed into a model. A junction with a proven ability to either stop or transmit destruction. 2 major faults now loaded to extraordinary levels. A corridor filled with people, highways, rail lines, and lifelines. And scientists looking at the results and choosing careful words that all point in the same direction. The system is critically stressed. The gate matters. The consequences of a joint rupture would be far greater. And Southern California needs to treat that reality with the seriousness it deserves. Because the most dangerous moment in a disaster story is often not the rupture itself. It is the phase just before it, when the warning still looks abstract, when nothing has visibly failed, when everyday life gives people permission to believe everything is stable. Cajon Pass is dangerous precisely because it still looks ordinary. That is how geological risk hides. In plain sight, under freeways, under train lines, under the routines of millions. Under a mountain corridor most people cross without ever thinking that beneath it, one of the most consequential earthquake gates in North America may now be closer to opening than it has been in centuries. So the next time someone says the San Andreas is the whole story, remember that fault systems are rarely that simple. Sometimes the real story lives at the junction, at the place where one rupture can become 2, at the place where geometry meets timing, at the place where centuries of stress accumulation stop being a background process and start becoming a scenario. That is why Cajon Pass matters. That is why scientists are alarmed. And that is why this may be one of the most important California earthquake stories of the year.